We do know that in metering techniques, we have many gases that are lighter than air. These are those gases: hydrogen, helium, hydrogen cyanide, hydrogen fluoride, methane, ethylene, diborane are illuminating gases, which are methane mixed with other gases like neon, carbon monoxide, acetylene, neon, nitrogen, and ammonia. Now, looking down this list, you might say, well, Jeremy, I'm not sure that there's a large prevalence of diborane or even illuminating gases. Illuminating gases used to be very common in light fixtures and exit signs and things. They're not so much anymore. I don't know how much neon's running around, but I can assure you there's a ton of methane, a ton of hydrogen fluoride, a ton of hydrogen, a ton of ammonia, a ton of nitrogen, a ton of acetylene, and a ton of ethylene in your jurisdictions right now. If you look at their vapor densities, let's just start with hydrogen. Its vapor density is 0.07 versus hydrogen cyanide, which is 0.93. So in relationship in total volume of air, hydrogen is going to be moving very high very quickly until it's hit by a cloud or a stop, like a ceiling. And even then it's going to be working its way through cracks to move up. So when we look down to carbon monoxide, which is a common call we make a lot, its molecular weight's 28, but its vapor density is 0.96. So it's pretty much equivalent to 1 or to air. And remember, vapor density is everything in relation to 1 being air. Air is a combination of multiple gases that have been compressed together. So where would we find carbon monoxide? It's marginally lighter than air, but because it's marginally lighter than air, kind of like how hydrogen cyanide is, they're going to be very susceptible to air currents. So wherever we find air moving or air collecting, turbulent airflow, look in the higher headspace of that area, and that's where you're likely to find your carbon monoxide. So when we're going into a house and we're wielding that meter and it's right in front of us at about waist height, and you're like, hey, I've got 30 part per million of CO, if there's not a lot of introduced ventilation into the area, the most prominent place we're going to find that CO is going to be a little bit higher up into that vapor space. So be sure to go there. Because of this, and these are the only gases that are lighter than air, every other gas should be easy to find at waist level or lower. This is very important. I made a hazardous materials call many years ago in a train derailment, and there was an HF car that had derailed. Many cars had derailed, but that was one of them. And there was one that I believe was either cyclopentane or cyclohexane. Either way, it ends in ANE, so we know it's a flammable gas. And it had been leaking next to the HF car. And gas metering had been done for HF and for our 5 gas senses. But right next to where the HF was leaking was this, and this gas was much heavier than air. So it wasn't until the entry team put the meter all the way down to the ground at where the base of the rail car had met the ground where it had derailed that they found a flammable environment. So if hot work had to be done, like welding on a removal cap or a removal stinger for the HF product, and that had not been done at that ground base, you could have easily agitated that environment, moved that area of explosive vapor to its LEL right around where you're working and cause an explosion. So don't ever forget the importance of metering down low, and that these 15 gases are the ones that we're going to see that are going to be high, and everything else should end up even or low. A way that you can remember them is the acronym 4H MEDIC ANA. So 4H would be our 4H gases, which are hydrogen, helium, HCN, and hydrogen fluoride. Just remember, HF is one of the nastiest substances on the planet. It is violently reactive to air, water, puppies, kittens, hope streams. It's pretty nasty. Hydrogen is very common. It's used as a cooling agent, so we have that pretty relatively prevalent in our jurisdictions. HCN, we know where that comes from. It's not only a weapon of mass destruction, but it's something that hurts a lot of firefighters on the fire ground as well. And of course, helium storages is something that we see pretty common. The MEDIC is going to be this part: methane, ethylene, diborane, illuminating gases, and CO, things that we deal with on a pretty regular basis. At least 2 of these guys are things that we are dealing with probably daily, weekly, if not daily. And then the ANA is going to get your acetylene, neon, nitrogen, and ammonia. Nitrogen and ammonia are ridiculously prevalent in our jurisdictions. Acetylene, we know we have that in shops and torches and things, and definitely in the urban search and rescue environment. So as we're looking for our metering and techniques in our priorities, we need to be looking at these guys because many of these have flammable signatures like acetylene, ammonia. Even though ammonia's lower explosive limit's 15%, it still is flammable. So be wary of those. When we're getting into interpreting alarms, because this is probably the most important part of this presentation, usually what I'll see is someone's wielding the dope in the rope or the dummy in the suit, and they're wielding this meter, and it starts making an alarm. They just look at it, and they just continue to look at it as if by depth or breadth of virtue of looking at it, the alarm's just going to get scared and stop. That's not how they work. The alarm is alarming for a reason, and so because of that, it requires your attention. So let's review some of the alarms that we're going to be dealing with, especially within the task force, but also within your jurisdiction, the meters you may use. Low limits, high limits, stells, TWAs, motions, max, and pumps. So low limits. Low limit alarms are designed it's a low limit that says, hey, listen, dummy, there is a presence of a vapor here, a gas here, and I need you to either start to think about what you're doing or to catch your attention. We're not at a level where we're dangerous yet to where you're going to be incapacitated, but we're at a level to where it should not be normal based on atmospheric conditions. In our toxic gas sensors, those low limits, or the meter starts at 0 and works its way up. The first alarm you're going to get hit is a low limit alarm. A low limit alarm says, I'm trying to catch your attention. With our oxygen sensor, it's a little bit different because our low limit alarm is anytime the oxygen gets below 19.5%, and the high limit is anytime it gets above 23.5% in the IDLHs. In every other toxic gas or electrochemical sensor, it starts at 0 and the low limit's going to move its way up to, hey, I'm trying to catch your attention. When we get to a high limit alarm, it's saying this gas concentration, regardless of what it is, a flammable gas or not, is dangerous, and it requires you to be in PPE to be able to keep moving forward with what we're doing. A STEL is short-term exposure limit. This is a term that was defined by the ACGIH, the American Congress of Government and Industrial Hygienists. And basically, we know that in the industry, people work with toxic gases all the time. And they do so without personal protective equipment, without respiratory protection. So the ACGIH has established STELs, which is basically is how long you can work next to a specific toxic chemical for no longer than 15 minutes with 60-minute rest cycles, no more than 4 times in a day. You're like, that's a lot. And it is a lot. It's less important to us because most of the time in hazardous materials, we are wearing personal protective equipment. However, if we have an STEL alarm and we're involved in a breaching and breaking scenario, and we're using concrete saws that are off-gassing carbon monoxide, and we've hit our COSTEL, it's saying that, listen, based by every single bit of literature out there, and the ACGIH is actually pretty conservative pretty liberal on their exposure amounts. Based on all the information known by all the people who do this, they're telling you that you should be upgrading your PPE to self-contained breathing apparatus. So that's an important thing, because if we're in that confined space and we're going for the win, and we're downrange and we're going for the win and we're trying to make this happen, if you're not going to be the person that pays attention to that STEL alarm and actually does something about it, you're wrong. Now, here's the problem with STEL alarms. Once it's alarming in most all of our meters and their configurations, it doesn't stop alarming. You have to remove the meter from the environment, clear the alarms, turn it off, power it back up, and go. So it's hit that STEL, and it says you've got too much of an exposure. If we're working in PPE, and we're there, and we're in, let's say, a self-contained breathing apparatus, and we're in an area of a high VOC or a high CO, and we've hit our STEL, there is no way to shut that thing off unless we go into the meter, we go into the alarm limits, and we expand those alarm limits. Like out of the factory, there's some STELs in your VOCs that are set to 10 part per million. So 10 part per million is pretty easy to get to in a 1,000 part per million concentration of a toxic chemical. So as a hazmat responder, you need to be smart enough to be able to get into that meter and turn off those alarms by changing alarm limits for mission-specific needs only. For general non-protective USAR and personal and fire department work, we never change alarm limits because they're set there to keep you protected. The TWA alarm, or the time-weighted average alarm, is that same, every chemical that's toxic as a TWA. It's how much of that chemical you could be exposed to on an average of 8 hours a day, 5 days a week, to 40 hours in a work week. So if you meet that threshold, which that's mathematically put into the meter, then that alarm will go off, and basically if you're not, in personal protective equipment that would protect you from that chemical, you need to change your operational posture and go to that immediately. We also have a motion alarm, a max alarm, and a pump fault alarm. Motion alarms are existent in some of these guys. Basically, it's a pass device. Almost all of our meters in the market now, you can set a pass device to where if we have a worker who's in a confined space and they don't move for a while, that pass device will go off. But if we're using an integrated SCBA with an integrated pass, it's pretty much not needed. But you should be aware that that motion alarm may be set up. Our max alarm, this will happen when you have reached the maximum detectable amount of a specific sensor, i.e. your oxygen sensor. You're going to get the high limit because you've got above 23.5%, but if its high limit is also 25%, you're going to get another alarm saying, hey, I can't go any higher than this. I have no idea where you are beyond this. And then a pump fault alarm on pumped-based meters. Anytime that you occlude the pump, you're going to get an alarm that says, hey, you occluded the pump. Fix it. And that can easily happen depending on how you carry it, how you store it, how you mess with it. How do we prevent nuisance alarms? Well, one, span calibrate at recommended intervals. Keep the meters honest, right? So if your manufacturer says they should be span calibrated or calibrated each sensor one time per month, then do that. Bump test prior to going into a threat area. Every manufacturer recommends bump testing prior to going to a suspected or known threat area. Usually, operationally, we just do that every day because most people don't carry cal gas on their apparatus, so it's easy to do it at the fire station so that we don't have to do it when we go down range. If you want to do it to the bump test and when you go to perform work with it, you'd have to keep your cal gas with the meter, and logistically it's difficult for many departments. Always perform a fresh air calibration on every time that you start up. When I say fresh air, I mean actual fresh air, not in the bay next to the fire truck after you just turn it off, not outside next to an idling fire truck, not next to an idling generator. It needs to be an actual fresh air. Be mindful of how you carry and hold the meter. You can easily occlude the pump panel or the pump inlet, which will cause a pump meter. You can also bump it around. If you jostle the sensors, you can change where the anodes are actually placed in the electrochemical sensors. It'll cause sensor faults. And be able to fix alarm limits on the fly if you're a hazmat specialist. Some common values you might see. These are usually pre-programmed, but don't worry, they can be changed. Our O2 limits are there. Our CO, usually our low limits are going to start at 35. 70 is our high limit, but look at those STELs. The STEL, the short-term exposure limit of CO, is 200 part per million. I am far more concerned about an STEL or TWA alarm than I am about a CO low or high alarm. If I hit the low alarm, it's saying you're working somewhere where CO is way higher than it should be ever. When I get to the high alarm, 70, it's saying you probably should think about going to SCBA because you're going to be hitting your TWA or STL soon. Other ones we see if we go to the bottom, like our LEL, you'll get 10% of an LEL or 20% of an LEL is a low and high limit. 10% is action level, 20% is you should have already solved the action. And then, of course, our PID, our low limit may be set to 100. Our high may be 200 part per million. But again, those STELs could be set at 10, 20, 15 part per million. So I'm just going to run through the basic alarms, and we'll wrap this up. On oxygen alarms, if it's low, that means oxygens have been displaced or consumed. So think about the presence of other gases that could have pushed oxygen out of the big picture. And consider that there could be a oxygen reaction or a chemical reaction that's consuming that oxygen. For the high alarm with oxygen, anytime it's greater than 23.5%, something is grossly wrong. There is nowhere in this in our atmosphere, in our Earth, where it naturally has a high oxygen concentration above 23.5%. So something would need to be significant leak of like a vapor oxygen or liquid oxygen, like maybe we're responding to a medical facility and a mainline oxygen from liquid oxygen has ruptured and it's rapidly expanding and causing vapor oxygen to be in the atmosphere. That's a huge problem, but it's also easy to figure out the source. If it's not that, consider that maybe we've met the SADT of an organic peroxide and a redox reaction is happening. So the self-accelerating decomposition temperature. So basically in a oxidizing or redox reaction, that organic peroxide has begun to undergo a chemical reaction where it's created enough external heat, and that heat is supporting its own self-degradation. And so you now have a runaway chemical reaction that would create more oxygen. If you were in an open area and you had higher than 23.5%, you're in a huge problem because if we've created that much oxygen in an open area, even in a room to do that, you've got big issues. But if we look at like closed atmospheres, containers, pipes, vessels that get above 23.5%, that's also really concerning, but you're at least in front of the problem. So if your oxygen sensor was saying, hey, we are at 16.9%, that doesn't mean you moved oxygen out 4%, so the other 4% is CO2. That means that you moved the oxygen out by 4%, and you had to move 16 other percent around that because oxygen is 1/5 of the atmosphere. So if you're looking at a 1% change in the oxygen concentration, like maybe it's 19.9%, you're looking at a total 5% change of volume in space to move out the nitrogen and other gases. That's it's a pretty telltale factor. With LEL alarms, again, 10% is usually set to our low limit. That's your action. Do something about the problem. If you hit 10% of the LEL, you need to be thinking about doing something different. If you get 20% of the LEL, whatever you're doing is not working, do better. And remember that you have correction factors for gas unknown. So like looking at this meter right here, you have H2S, 0 part per million, CO 0, oxygen 20.9%, so that's normal, but you have 10% of an explosive compound there of the lower explosive limit. If it was methane, that means that you're at 0.5% of 0.5% of getting to the total concentration by volume. But that's only if it's methane. We use correction factors because this is only calibrated to that. If we're in a gasoline leak, let's say a styrene leak, styrene's correction factor for multi-ray, I think, is 2.8 times, which means you'd have to times that number by 2.8 to get an actual representation of how close you are to the LEL. So that would be, if the meter's saying 10%, you're actually at 28% of the LEL. So you're past the action limit. You're in the area where you should have done something to fix the problem. So in unknown gas concentrations or unknown gas amounts, I always say, hey, listen, on the correction factors, multiply it by 3. That's a good conservative number to keep you and your team safe. If you know what the gas is, apply the correct correction factor. In the task force, our multi-rays can easily be opened up and we can apply correction factors on the fly and correct for the known gas that's with us. In CO, looking at this alarm display, we've got 60 part per million. So you're going to see 35 part per million in our meters and our multi-rays as our low, 70 as our high. So this guy, you can see this one's set to the high alarms going off at 60. It's telling you that you're about 14 times or less the way to getting to the IDLH, but you should be thinking about an SCBA. Because in very short order, you're going to be working in this environment, in very short order, you're going to hit your short-term exposure limit or the limit to where you could start seeing biologic and health effects from that exposure. H2S alarms, very uncommon. They're very uncommon by themselves. H2S has a lot of cross sensitivities. So when you're using things like multi-rays or Dragers or Industrial Scientifics or RKIs or black lines, look at the literature and see what the common cross sensitivities are for their electrochemical sensors, because it may not be H2S, it may be something similar to it. However, H2S has a odor threshold of 0.008 ppm to 0.1 ppm, so most people can smell it. Well below it becomes a problem. We said its IDLH is 100 part per million, so we can smell it 1,000 times before it becomes a problem for us. So if you can't smell it, or if you're in SCBA and we're not able to smell stuff because we're in supplied air SCBA, or the odor threshold doesn't apply to you, just be wary of the fact that we need to meter and monitor for that. As far as our VOCs goes in our PID detector, just remember that the PID is not always picking up VOCs. There are lots of inorganic or volatile inorganic compounds that it will also detect, but the 99 or probably the 90% mark of things are going to be volatile, carbon, compound, and base. If you're getting a hit on the VOC, you should also be thinking about being flammable. Now, having said that, if we have 100 part per million of isobutylene's flammable at 16%, you still have 16,000 part per million to get to. And if you're picking it up at 100 part per million, you're still way far below even the meter's ability to pick up a percentage shift. So you will see things in VOC far before you'll see them in percentages of CGIs. Correction factors for PIDs are way more important because there are many correction factors that can be 10 times the displayed number. So if it's an unknown chemical or something far different than isobutylene, which I doubt you're making a lot of isobutylene leaks, just remember that whatever your PID is saying, it's probably incorrect. It may be higher than what's actually there, and it could be lower. So if you can't establish what the substance is, you can't use the PID to accurately quantify the environment. You can use the PID to accurately qualify that you have something that we know is off-gassing or volatile. It's likely carbon containing, and it's most likely a compound. And we know it has an ionization potential of 10.6 or less, or whatever your bulb voltage is. So for other toxic gases, like this is an ammonia detector here, just use the actual percentage to be specific to the exotic gas. Our specific toxic gas sensors are far more expensive and usually have a little bit less of cross-sensitivity, but that doesn't mean they don't have one. I have seen many a chlorine sensor get bombarded with an acetone and give me 6, 7, 8 part per million of chlorine. The IDLH of chlorine is 10 part per million, and you can be in a non-existent chlorine environment and have other flammable liquids and noxious vapors that are causing cross-sensitivity. So as like everything else, use the totality of the circumstance. If we're next to a 1017 container with a UNID of 1017 that's chlorine, the chlorine sensor is going off, we have a greenish white cloud, and we have paint that's bubbling next to the wall, yeah, it's probably chlorine and probably not acetone. So to review, just note the best hazmat and USAR professionals out there, they have a strong familiarization with their equipment. Regardless of what team you're a part of and what you do, you should have a high command of what the equipment is that you're working with. And when you leave the task force and you go back to your normal day-to-day operations, just be the best at what you do. Stay current with your specific metering platforms. Know what they do, but more than what they do, know what they don't do. Don't tell me an atmosphere is okay when you don't have the correct equipment to rule that out. And lastly, remember, if the meter is making a sound, it's because it wants your attention. Do not ignore your alarms. Look at it, and in worst case scenario, call an adult. I hope this was informative, and I'll talk to you guys later. Thank you.